So this is lab 4 for physics 2211, biomechanics Ekaterin. And here's my video report. First introduction, purpose. The purpose of the lab was to analyze and predict motion of a spring spin. So we have mass oscillating in an arc and at the same time oscillating on the spring. So there's two oscillations there. It's hard to usually predict it. So here we try to prove that we can do that. Models, we use a glow script model written in Python. Principles, we use energy principles such as conservation of energy, kinetic energy, spring energy, gravitational potential energy, and of course our favorite Newton's second law. Assumptions. Our assumptions are that there is no air resistance and no energy transfer to surroundings, so the energy is not leaving the system. Preview of the results is at the right with those graphs and model. So, system and surroundings. Our system is mass and a spring. Surroundings, spring attachment, and air. Initial conditions, ball is radius with no initial spin, and here's the initial conditions. You can see the ball mass, 0.402, ball position, ball velocity 0, no initial speed, gravity of course, the K of the spring, and the relaxed length of the spring. So here's tracker. What did we do is to take the video of spring in motion, take tracker, track its motion, get the data. Then we have a glow script model where we used the initial conditions and modeled the motion of the ball mass. Then we used, here's the code. Then we uploaded the data from the video and we got these graphs. At right, that's graphs of x position and y position against time for the model against the experiment. And at the left, you can see the energy changes in the predicted by the model. So, sources of error, that could possibly be because we see that from the graphs that model and experiment are not really matching. They are, well, they're really close, but not really. The amplitude is more for the model usually, and it's all a bit off. So the sources of error are possibly for no account for area resistance, energy transfer between spring and its attachment, so we lose energy. As we can see, we can see that in the y position. We can see that the amplitude of the experiment line is gets lower by time. So yeah, we have actually energy leaking out, and also of course tracker. There can be human error in tracking the position in tracker. So what does that mean? First question, for your model system, is energy principle satisfied? Yes, because the delta E is constantly at 0 at the graph. So energy is preserved. What does that mean too? Using the data you obtained in tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the exposition data, and second, by estimating the period of oscillation compared to estimates and discuss. So from the two graphs, I estimated that for experiments, both period for x and period for y equal to approximately 1.6 seconds. So they're the same, which proves energy preservation. So if the period is the same, the energy will lose in x direction or goes to y direction. So yeah, that's why they're the same, I guess, as far as my knowledge tells me. So that's all. Thank you for your attention. Yeah.